So I'm pleased to be here. I almost feel like cheating because I'm not fully a CFHT user yet. But I do have ideas and I really want to welcome dialogue. So that's why I'm here today. So I'm going to talk to you about optimizing discovery, in this case for community surveys. And I'm here on behalf of NOIRLab, which has a big suite of facilities. They are not as crowded as on this image. And like I said, I really want to introduce a bit about our own experience with community surveys, large public surveys, and hopefully initiate discussion over the remaining time here. So in terms of facilities, we have a number of telescopes. We're primarily based headquarters in Tucson, Arizona, but we have Chile and Hawaii. And some of these programs would not be possible without partners. So we're not, working alone here, especially Gemini. We have international partners. And for the Rubin Observatory, it's also a partnership between NSF and the DOE, Department of Energy. But we also have telescopes on Kitt Peak in Arizona, and then Cerro Tololo in Chile. And then CSDC is a community science and data center. So I'm here because data and software are very important. So we don't just think of which filter, which area. We have to think all the way to how we're going to handle all these data and the software. So I do want to advertise a few things, some of which you may already know, but we have just recently expanded the time available for larger programs or survey programs of our mid-scale observatory, so 4-meter class. And then the Gemini Large Unknown program has been ongoing. And then more recently, there's also a NASA NSF Exoplanet Observational Research, and that's again a partnership, different facilities. And then more recently, we had the DESI DR1, which at NOIRLab we're serving a copy and we're serving additional ways of using that data. So that's also important. Okay, so I will talk a bit more about the data system, again, data and software that go with the surveys. So the Rubin Science Platform is obviously the biggest and latest, but I'm not going to talk as much about this today. I want to advertise the fact that already with the other NOIRLab facilities, especially the wide field cameras and the Astro Data Archive, slowly over 30 plus 40 years, we actually have been building quite the collection of data now. So this map is the sky coverage as of a year and a half ago. And then, but we recently have already 3 petabytes of images. But this is all available in the archive, now publicly available. And we also serve some high-level science products. And separately from that, there's a Gemini archive, obviously not as large because it's not as big, survey images, but still a big resource and with a lot of interested users here. And I think there's a lot of value in providing not just the data, but the reduced process data with tools. And then at the moment, we don't offer reduced data for everything, but these are some of the pipelines that exist. Okay, and then beyond having archives where people can go and connect and use the data, similar to JJ's talk earlier, we also have science platform. So ours is called the Astro Data Lab, and this is similar, but not quite the same as the Rubin Science Platform. The idea is that these two will still be compatible with each other. But this started way back in 2017. And then this map here is color-coded by the number of queries to our Astro Data Lab database. And then the reddest color is between 10 and 100 million queries. And I think this is for 1 year. This is for 2024. So you can see that we have a number of users and they're geographically distributed. And then just recently we added the DESI spectra, and I'm going to say a bit more in a couple of slides. But just to show you the data lab, the Astro Data Lab in a nutshell, we have large catalogs which are put into a database so we can search and access all these and cross-match them. We have pixel data so users can find images of their objects of interest. And then there's visual storage. We do offer 1 terabyte per user of storage. And this is free. Okay, so, and then compute processing. There is no supercomputer, but we do have, some reasonable amount that you can work basically on our machine, so you don't have to download anything. So you can connect. We have a Jupyter Lab and also other ways for data visualization. Okay, so the data sets that we currently have kind of fall in three different categories. Some come from our own NOIRLab telescopes, and I'm not going to go through the list, but just to illustrate, some of them, like from the dark energy camera, for example. But we also have external data sets like Gaia, SDSS, WISE, all things that could be useful for combining to do multi-wavelength studies. And we also started having simulated data sets of simulated LSST surveys. And this is a visual representation for some of these data sets again. So on the left-hand side, you have equatorial coordinates, the legacy surveys. And then these are just to illustrate, the rest are in galactic coordinates. And then the bottom right is a simulated data set here. So just to show that there's some variety of data set in there, I think one of our main strengths that I'm the most proud of is that we spend a lot of time and effort to develop very good example tutorial notebooks, all the way from, high school education outreach to professional research level. And these include, different topics that we try to make sure that each data set at least one example to be paired with. So this actually is a lot of work, but I think it's very rewarding because it's a useful thing to have. I do want to advertise, because this is kind of my baby project right now, Sparkle. So we have spectra in the database. Mostly we have large spectroscopic survey data here, so DESI and SDSS at the moment. One thing we would like to develop is a way to keep adding more spectra into this database so that somebody could say, hey, I'm looking at this object in this piece of sky, are there spectra of any kind? So this would probably require more work and maybe a bigger network and more collaborations. But so far, this has been a fairly new service. And then I'm going to show a couple very quick use cases just to give you ideas. But this was a simple case that we just basically made to demonstrate how it works. So you query the AstroDataLab and you say, okay, I'm going to look at SDSS. Give me n stars in these 8 bins of color. In the first case, n is 10. So we just do 10 stars random in bins of color. And then we stack them. So these are, on the left-hand side, you can see these 8 different colors that I've expected, blue to red. But this is just to show that it takes 5 seconds to do this. So you end up getting 80 spectra of stars. And then to get 500 per bin, so that's 4,000 spectra, that takes 90 seconds. But we can just, this is not a real science case again. This is just to demonstrate the tool and the timing. But it gives also an idea of the kind of spectral quality. So this is again this one is from SDSS here. A more recent example use case, and I'm showing, unfortunately, a reject figure that I myself made, but the first author chose not to include it, but I'm showing it anyway, because I like it. But the paper is actually very interesting. So recently, this is led by Anthony Taylor et al., and we just found with JWST the most distant quasar with a broad line, well, AGN, I guess, at redshift 9.3. And then it has a broad age beta. So it's the black line. 1 minute. You can see the broad age beta. And then the question was, okay, are there any quasars that look like this redshift 9 quasar at lower redshift? And this is currently the best sample to search because it's even larger than SDSS. So these were lots, huge numbers. So I thought, okay, I can do this with DataLab and Sparkle. So I'm going to force to have similar age beta in O3. So the relative strengths, the widths. So how many spectra are similar in all these properties and the luminosity of the O3 line? And that should go from, millions spectra to like 200, so manageable. So that, okay, I can plot out 201 figure. So it took just 5 seconds with Sparkle to retrieve 200, and then I could put them on this plot. From red to blue, I use a little synthetic color. But then the result of this comparison is even the reddest spectra in DESI, they don't even look like the high redshift. So there's no analog. There's nothing like it as far as you can tell here at lower redshift. What does it mean? Stay tuned. I don't know. Okay, so this is my last 10 seconds. So this is just to illustrate what's happening now in the way we do research, right? The traditional circle, you have your idea, you need to learn some skills, and then you eventually formulate your question to write a proposal that gives you the data, analyze the data, interpret and publish. And then we go round and round and round for our career, and we have such a great time doing this. But there's also another way. When we do these open data models, so from community surveys, we can speed up that cycle, so we can already make the data available. So you can shop with your idea, but you still need to have some skills and expertise, and then you can use the data and go ahead and go around faster. So in our case, we have the CSDC and then Rubin coming for this kind of mode, but obviously with CADC, it's similar with CANFAR and CFHT as well. And then the latest thing that we've been developing is we're now part of an AI institute it's an NSF Simon founded Cosmic AI. And then the idea is to even accelerate research even further. So we want to provide AI tools, but at all levels to help gain the expertise faster, to help maybe process data faster. So the idea is really to even speed up this, as much as possible. Not that we're not busy enough, but to help that research. So you can ask me I think I'm going to skip this because of the time. And then time domain, obviously we've heard a lot about, but we're interested in this. So I'm going to leave it with my takeaway message. So I think it's very important as we prepare and plan community surveys to also plan about how we're going to serve the data and how we're going to provide tools. And probably it would be easier to do this in collaboration between different institutes, different science platforms working together. So this is JJ and me shaking hands here on the slide. Okay, good. All right. And I think if we coordinate, we can achieve more. And also the software effort needs to be planned in advance. So I was just going to reiterate that. I'm going to stop here.
Okay, maybe we have time for one quick question.
Thank you very much for a very interesting presentation with a lot of data. We like data. Victor Halak, Université de Moncton. I have just one small question with regards to the spectral resolution. So your spectra are like in the group, depending on which kind of spectral resolution we require. And another question about signal-to-noise ratio.
Okay, so what I was showing was this SDSF and DESI spectra. So those resolution is between 2 and 5,000, roughly this kind of number. So maybe, low, mid resolution. And then your question for the signal-to-noise. I guess I'm not sure what your question is, but the database has the inverse variance. So you can calculate the individual signal-to-noise per pixel. DESI spectra can go pretty low in signal-to-noise. So that's why some of the studies involve stacking or making composites. But there's also a lot of science that can be done either on their individual spectra or working on modeling them as an ensemble, like with machine learning or with other statistical tools. Optional. Great.
Okay, let's thank Stephanie again.